catalysts. Let's talk about what catalysts do. The equilibrium constant describes how far the reaction will go, the relative concentrations of reactants and products. It doesn't tell us how fast it's going to get there. The reaction rate tells how fast it will get to equilibrium. And that's going to depend on a couple of things. One of them is the activation energy. It's also called an activation barrier. This is the amount of energy that that the collisions must have in order for the reaction to occur. It's like a barrier that you have to climb over in order for the reactants to be converted into products. Most of these have to do with breaking bonds that are present before you can form the new bonds. So this is an energy diagram where on the y-coordinate energy is increasing as we go up, and here's the reaction pathway, similar to time, as time goes on. So here we're starting here with kind of an intermediate amount of energy. In order for the products to form, we have to break the existing bonds in these molecules, and that requires energy. So the energy has to go up, and once we break those bonds, then as the new bonds are formed, that releases a great deal of energy, and the products end up at a lower energy than the reactants did. Now, I think of this as, this reminds me of miniature golf. So I'm going to get rid of those guys. I'm going to get rid of these guys. And to me, this looks a little bit like we're playing miniature golf. And so here's some person, and he's got the little golf club there, right? And here's the golf ball. And down here is the hole where you want the golf ball to go. They put all these obstacles in the miniature golf course, right? And so you've got to hit the golf ball with enough energy to get it up and over the hump. Once it gets over the hump, it's going to go down the hill and everything's fine. But getting up over the hump is the problem. If you don't give it enough energy, it'll go partway up the hill and it'll roll back. And you will not get it over the hill. To get it over the hill, you have to hit it harder, right? So if you have a high activation energy, it's going to take higher energy collisions for the reaction to occur. If this activation energy is very high, is that going to make the reaction slower or faster? It's going to make it slower. If this hill was lower, what would that do to the rate of the reaction? It would make it go faster because it would be easier to get the ball over the hump, right? More of the collisions would have enough energy to get over the hump. So how can we speed up a slow reaction? Slow reactions have high activation barriers. So we have fewer reactant molecules that make it over the barrier because they don't have enough energy. So at a particular temperature, if you have a high activation energy, you're going to have a slow reaction rate. We just talked about that. How do we speed it up? Well, we could increase the concentrations of reactants because then we're going to get more collisions. Some of those collisions will be high energy, some low energy, but if there's more overall collisions, the number of high energy collisions will also increase and the rate will go up. The other thing we could do is we could increase the temperature. Increasing the temperature causes the particles to move faster on average. That increases the number of collisions, and more importantly, it increases the number of high energy collisions. And so that also increases the reaction rate. So we can increase concentration, we can increase temperature, or we can use a catalyst. And what a catalyst does is it lowers the activation energy. So it's like a bulldozer coming in and cutting off the top of the hump. Or it's an alternate pathway. Like, oh, well, you actually don't have to go over that giant hump. If you go over this way, you just have to go over a little hump. And so then people are going to go around the easy way on the miniature golf course. So here's an example of rocks, boulders on a hill. So you're pushing boulders up the hill, and it requires a lot of energy. And the rate of being able to do this is going to be slow. It's going to take you a long time to do this because you have to push the boulders up here before they can fall off the edge of the cliff. What a catalyst does, it allows you to have a lower energy pathway. You can go around the peak of the hill, and you just have to go over this little rise, and then you can get around it, and the boulders will fall. So that increases the rate of a reaction. A catalyst allows for an alternate pathway, a lower energy pathway. In the energy diagram, this is what happens. So here's the original activation energy, the barrier. A catalyst gives us a lower activation energy. And your body uses enzymes. Your body is a chemical factory. There's zillions of chemical reactions going on in your body right now. Most of them at normal body temperatures occur very, very slowly because their activation energies are high. But your body has enzymes, and the enzymes act as catalysts, and they cause a lowered activation energy, and they speed up the reaction. What's really cool about enzymes is your body can put out an enzyme when it needs this reaction to occur, and then when you've got enough of whatever that's producing, it can take the enzyme away and stop that reaction. And so the reactions can be controlled by the use of the catalysts known as enzymes. Yeah, I got ahead of it. Because in your body, you can't just increase the temperature to cause the reactions to go faster. And so you use enzymes to do that. Another analogy, oh, well, let's just stick with this. So sucrase is a catalyst. So here's sucrose. Sucrose is glucose and fructose. It's a disaccharide. And when your body metabolizes it, it takes it apart. And in order to take sucrose apart into glucose and fructose, there's a certain amount of activation energy that needs to be overcome at normal body temperatures. It's not going to happen very fast at all. Well, your body uses sucrase to strain the bond between these two saccharides and causes it to be much easier for them to break apart. And so it requires a much lower activation energy, and so the reaction is much faster. Again, got ahead of myself. So here's sucrose. An enzyme has an active site. So this sucrose molecule just kind of nestles in and fits in here. It's like, oh, this seat was made just for me. But in the process of doing that, this bond holding the two molecules together gets strained and weakened, and so that it's easier to break. That lowers the activation energy. And so these are going to break apart, and then the sucrase says, okay, done with you, spits them out, and then the sucrase can do that with another molecule. Catalysts are not reactants. They are not products. They do not get used up. They can go over and over and over again. I need to draw a picture. I have nowhere to draw a picture. I'll draw a picture here. So another way to think of this is, let's say we've got a fence. There's a fence out on the playground, and here's the line of kindergartners. They're short, right? Because kindergartners are small. And they're trying to get over the fence. They have to climb up and over the fence, and they're small, and so it's hard for them. And they're not going to get over the fence very quickly. How could we get the kindergartners over the fence faster? We could remove the fence. Okay, so this is a split rail, a rail fence, and what if we lower one of those rails? We slip it out and put it down. We've lowered the barrier. Now there's just this bottom rail, and they can hop over that much easier, right? So that a catalyst would do something like that. What else could we do? Well, we could put a teacher here. We'll stereotype and say the teacher's a woman. And as the children come, she could lift them up and put them over the fence. And that would be faster than waiting for all of them to climb over. In the process, that one teacher is facilitating the reaction for multiple children. She doesn't get used up. She doesn't go over the fence and disappear with the first child. She helps all of them. That's what a catalyst does. And there's, I skipped that one. There's your chapter in review. Those are things you should know.